So in this video I'm going to talk about an angled projectile from the ground level. So let's say we had like a cannon or something over here, and we were going to launch a cannonball from the ground at a velocity of, let's just say, 20 meters per second. And let's make the angle that looks roughly about 30 degrees. Right? As we launch this projectile, the object is going to fly through the air, right? And if we just follow its path, it's going to do this, and then it's going to arc down and strike the ground over here somewhere, right? And just keep in mind that this isn't like an accurate motion diagram, right? I'm just trying to show the trajectory of the cannon, okay? So similar to our horizontal projectiles, the first thing that we really need to do is we need to figure out the components. Well, for a horizontal projectile, we had the vertical component was 0, and the horizontal component was all of the velocity that the object had. However, if we're dealing with something being launched at an angle, we can see that some of the velocity is up and some of the velocity is forward. So there would be a y component here of the velocity, so it's how much of this total velocity is up in the air. And then the forward velocity, so how much is in this direction. So we would just start every projectile problem, or angle projectile problem, by finding the velocity in the x direction and the velocity in the y direction, right? So for this side, we've got the sine of 30 times 20, and on this side, we have the cosine of 30 times 20. I don't know why I put that in parentheses. Okay. So sine of 30 times 20, that gives me 10. That's 1/2. So this would be 10 meters per second. And then for this one, the cosine of 30 times 20, and that gives me 17.32. Right? So this is my y component, and this is my x component. After I have solved these two components, then I should never have to use this velocity ever again. So now 20 meters per second is irrelevant to the rest of the problem. So I can just completely forget about it, because we're going to treat our x's and our y's independent of one another, just like we did with the horizontal projectile. So what's going to happen to the x's is just like horizontal projectile, it stays constant the entire time. So the x component of the velocity vector is going to be equal to, sorry, I kind of drew that at an angle so you can see it, 17.32 the entire time. There's nothing causing it to accelerate as it's flying through the air. However, the vertical velocity is going to decrease, right, because it will be slowed down due to gravity. So the vertical component here will start large, and then it'll get smaller and smaller until right here where it's actually 0. So velocity in the y direction is 0 meters per second. And then it starts to get bigger in the negative direction, you know, all the way down here. So in the horizontal direction, so the velocity in the x direction is constant, and the velocity in the y direction accelerates due to gravity. So in our horizontal projectile, we're treating the projectile as it flew off as if it was a dropping problem, right? That the initial velocity in the y direction is 0. So similarly, when we deal with an angled projectile like this, we're going to deal with the y component as if it's tossing something up in the air, right? So let's try and figure out there's lots of things we can figure out. I want to know time in the air, so time in the air, so time, okay. Let's also figure out the dy, which would be the height that the projectile reaches. And then we could figure out dx, which would be the range the projectile reaches. So time in the air. Time, remember, is linked between both the x and the y component. And time is dependent on gravity. So just like we treated this like a dropping problem, let's go ahead and treat this like a tossing a ball up in the air problem. So here I've got my v initial in the y direction, and then up here I would have I could call this my v final up here. And I could determine, well, how long does it take for the ball to reach its max height? And then it would be equivalent time to strike the ground. So time up is equal to time down. And remember, we had that real easy equation that if you take velocity final minus velocity initial, all divided by a equals t, which is really just the change in velocity over time is equal to acceleration. But without really even looking, we can know, like, okay, that would be 0 minus 10 all over negative 10, which is 1 second, right? So that's the time up. If I multiplied it by 2, the total time in the air would be 2 seconds, right? And just by looking at 10 meters per second, I should be able to just move my decimal place once and multiply by 2, and that gives me the total time. Right now, I know that 2 seconds is how long something is in the air, both vertically as well as horizontally. So let's do the next part, which will be, I'll solve for range next. Right? So range is going to be dx, and remember that in the x direction, my velocity is constant. So all I'd have to do is take, well, velocity x is equal to the displacement in the x direction all over time. So if I multiply by t on both sides, I get that 17.32 meters per second times 2 seconds is going to give me 34.64 meters. So that would be the horizontal range. So just note that here I used this. One of the most common mistakes is that people want to continue to use this 20 meters per second after we've resolved the vectors. Right? So the next one, let's look at dy, how high up in the air. So again, I'm in the y direction, I have acceleration due to gravity, right? So I'm going to have a is equal to negative 10. I have t already, so I know t up to this point is 1 second, so I could use that. I know the velocity here, and I know the velocity here, so I know v initial and v final. So I've really got all of the information. I could use either of my constant acceleration equations, either bf squared equals v initial squared plus 2ad, or d equals v initial t plus 1/2 at squared. Let's use this one. So d is equal to v initial t plus 1/2 at squared. And let's go ahead and treat this like my initial velocity. So that would make that whole term cancel out. I'm going to use 1 second because it would be half the time, because 1 second has passed for it to get to this point. So I would just get that dy is equal to 1/2 of negative 10, as if I was dropping it from up there, right? And then 1 squared, which makes this really easy. So I know that the height would then be 5 meters. All right, so the moral of the story is that when we do projectiles, you always start by resolving the x and y components. The x in the x direction, the velocity is constant, so we can just use this equation, just like we did with our horizontal projectiles. And in the y direction, there's acceleration due to gravity, so we're going to use our constant acceleration equations, and we treat this like a problem, just like the problems where we were tossing something straight up in the air. Okay. Now there's one more conceptual thing I kind of want to talk about before I end this video. Right? So let's say I launch something at 30 degrees. Right? It's going to fly through the air and kind of fly close to the ground and then strike the ground here. If I increase the angle to 45 degrees, it's going to be up in the air for longer, but it's also going to have more horizontal component of the velocity vector. So that would be a further range. Right? Then if I were to increase, say, to 60 degrees, now what I've done is I'm launching more straight up in the air, right? So it's going to increase the time that the object's up in the air, but it decreases how much of your velocity vector is pushing it forward. So if I were to draw, let me go ahead and redraw these dots right here for the first one so you can see this. Okay? If I were to draw something launched at 60 degrees, it would go like this. Right? So it would land in the same spot if it was launched at 60 as if it was launched at 30. However, what would maximize the range, the maximum range anything could shoot, would be launched at an angle of 40 degrees. So max range, not 40 degrees, sorry, would be launched at 45 degrees. However, the range at 30 degrees would be equal to the range at 60 degrees. All right? So in the next video, we'll look at what happens when we launch an angled projectile from some elevation. Come on, skin.